Hi friends, in this video we look at the last stop in our journey, the modern periodic table. Remember in the previous videos we discussed the earlier attempts to classify elements, that is the Dobrynin's triads, Newland's law of octaves and Mendeleev's periodic table. Here we are going to look at the modern periodic table, but we are going to do it in a different and interesting way. So rather than starting with the periodic table, we are going to start with a blank table and we'll fill it up as we go along in this video. I'm sure by the end of the video, you'll be a master of the periodic table. And as usual, we'll finish off with our top 3 questions on this topic. Normally, when you draw a table, it looks something like this, with rows and columns. But if you take a look at our periodic table, it has a strange shape, and we are going to see why. As I said, we'll start with a blank table and we are going to fill it up as we go along in this video. Since our focus is only till the 20th element, which is calcium, so we'll be looking only at the first 4 rows of the periodic table. Let's call this our mini periodic table. We'll talk about the lower rows later on in this video. So I'd like you to pause the video here and go ahead and sketch our mini periodic table in your notebook. Just draw this blank table till the 4th row. You can also pause the video here and do a print screen and take out a printout of the blank table. Friends, are you ready with your blank periodic table? I'm going to magically shrink myself so that you can see this table better. And let's fill up this table together. First, let's start by numbering the rows. So it's going to be 1, 2, 3 and so on. In our mini periodic table, we have only 4 rows. But the full table has 7 rows. Rows are called periods. So these are period numbers. Similarly, we can number the columns. So the column number is going to be 1, 2, 3 and all the way up to 18. Columns are called groups in the periodic table. So these are our group numbers. There is a different numbering scheme for groups as well, but we'll look at that later on in the video. Next, start numbering the boxes. So start from 1, 2, finish the first row, then go on to the second row, 3, 4, 5 and so on. These numbers look like serial numbers or roll numbers, but do you know what they really are? That's right. They are atomic numbers. Atomic number is defined as the number of protons present in the nucleus of an element. This was the major difference between the modern periodic table and Mendeleev's periodic table. Mendeleev's table was based on atomic mass, but the modern table is based on atomic number. Now you may be wondering why. Because the scientist Moseley proved that atomic number is a more fundamental property for elements as compared to atomic mass. So the chemical properties of elements are more related to their atomic number than their atomic mass. Next, let's start filling in the elements in our table. So do you know which is the first element with atomic number 1, with just 1 proton in the nucleus? That's right. The correct answer is hydrogen. So let's put the symbol of hydrogen H in the first box. Next, with atomic number 2, we have helium. And now let's go down to the second row. So there we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And I want you to fill up all the way till element number 20. So that is till calcium. With every element that you filled in here, the atomic number is increasing by 1. So what does that mean? 1 extra proton is being added in the nucleus. Now how is the electron number changing? What do you think? That's right. The electrons are also increasing by 1 because remember, an atom is neutral. It has equal number of protons and electrons. And note, we are not concerned about the number of neutrons right now. Now let's talk about the significance of the period or the row. So in our mini periodic table, we have periods from 1 to 4. But remember, in the full periodic table, you have it up till 7. So what does this period number tell us? It tells us the number of electron shells or electron orbits present in an atom. So we can predict the number of shells without even drawing the electronic structure. So let's take some examples. Hydrogen is in period 1, so it has only one shell. Now if you look at oxygen, it's in period 2, so it contains 2 shells. So similarly, how many shells does aluminium have? That's right, 3 shells, since it's in period 3. And what about calcium? Correct, 4 shells. It's in period number 4. So with every new period, one more shell is being added. Now let's verify this by looking at the electronic configuration of a few elements. Let's draw the electron configuration of hydrogen. It has atomic number 1. So just one proton and one electron. And as you can see, it has only one shell. Next, let's look at oxygen. It has atomic number 8. So that's 8 protons and 8 electrons. So if you draw its electron configuration, the first shell will have 2 electrons since it can hold maximum of 2, and the second shell has 6 electrons. So as you can see, oxygen is in period number 2 and it has 2 shells. Next we have aluminium with atomic number 13. So the electron configuration is going to be 2, 8, 3. So aluminium in the third period has 3 shells. You can draw the full electron configuration or you can write it in this simple comma notation, 2, 8, 3. And let's also look at calcium, which is in the fourth period with atomic number 20. And as you can see, its electron configuration is 2, 8, 8, 2. So as expected, calcium in the fourth period has 4 shells. Now let's discuss the significance of the group. We always try to group similar things together so that it's easy for us. A simple everyday life example is the grocery store, where you'll find similar things grouped together. For example, you'll find all the vegetables together, salt and sugar on one side, and all the chocolates in one place. Now imagine you walk into the grocery store and everything is scattered. You'll go crazy while shopping, right? Similarly, in the periodic table, elements having similar chemical properties are grouped together. Now let's take a closer look. If you look at group 1, except for hydrogen, all the elements in group 1 are metals. They are called alkali metals and they have similar chemical properties. They have the same valency 1. Now let's look at group 2. Once again we see there are metals in this group. They are called alkaline earth metals and they also have the same valency. Now let's move ahead to group 17. If you look at this group, it contains non-metals and they have the same valency 1. Now an interesting question is, why do elements in the same group have same valency and similar chemical properties? What do you think? Well, the answer lies in how the electrons are arranged in the atom. That is the electronic configuration. So let's go ahead and analyze the electronic configuration of elements in the same group. Let's start with the group 1 elements: hydrogen, lithium, sodium and potassium. They have atomic numbers of 1, 3, 11 and 19. Now let's try to write down their electronic configuration. Hydrogen is simple. It just has 1 electron. Now lithium has an atomic number of 3. So it's going to be 2, 1. Sodium will be 2, 8, 1. And potassium is going to be 2, 8, 8, 1. So can you see what these elements have in common? That's right. They have just 1 electron in their outermost shell. So that's 1 valence electron. So all these elements have the valency 1. And why do they have similar chemical properties? Because chemical properties depend on the number of valence electrons, which is same for all these elements. Now let's look at group 2. Here we have beryllium, magnesium and calcium. Similarly, let's write down their electronic configurations. So beryllium with an atomic number 4 is going to be 2, 2. Magnesium, which has an atomic number of 12, the electron configuration is going to be 2, 8, 2. And calcium, which has 20 electrons, is going to be 2, 8, 8, 2. So once again you can see all these elements have the same number of valence electrons, which is 2 in this case. So they have the same valency, 2, and hence they show similar chemical properties. In summary, we saw that elements belonging to the same group have the same valency and similar chemical properties because they have the same number of valence electrons. Now the group numbering that we saw from 1 to 18 is the new scheme. There is an older scheme that uses Roman numbers and alphabets A and B. Let's take a look at the old scheme as well. As we have seen, the new scheme has group numbers from 1 to 18. Now let's look at the old scheme. Group 1 has the number 1A. Note 1 is written in Roman numeral and the alphabet capital A. Group 2 is 2A. Now when we go to group 3, it's tricky. It's going to be 3B. Then you have 4B, 5B, 6B, 7B, and groups 8, 9 and 10 have the Roman number 8. Then group 11 is 1B, 12 is 2B, and then when you move on to 13, it's 3A, 4A, 5A, 6A, and group 17 is 7A. And the last group, group 18, has the number 0. The new group numbering scheme is much easier to remember than the old one. But it's important to know the old one as well because sometimes it's used. Now I can teach you an easy trick to remember the mapping between the new and the old scheme. Basically, you have till calcium in your syllabus, element number 20. So if you take a look, you have group 1, group 2, and then group 13, 14, 15, 16, 17 and 18 in your syllabus. You don't have the groups from 3 to 12. Now if you look at the old scheme, so what you have in syllabus is 1A, 2A, and then 3A, 4A, 5A, 6A, 7A and group 0. So basically only the A groups are in your syllabus and group 0, which is the noble gases. The B groups and group 8 are not in your syllabus. So I hope that helps you remember the old scheme. We have a lot of details in our periodic table. Now let's go ahead and add some color. You might have seen these colorful pictures of the periodic table, where the colors represent the different types of elements. For example, metals, non-metals, noble gases and metalloids. So are you ready to start coloring our periodic table? First, let's color the 4 broad categories of elements: metals, non-metals, metalloids and noble gases. Now our periodic table looks more colorful, right? But you might have seen some other periodic tables which have more colors and some different colors in different groups, like this picture here. So let's go ahead and take a look at some of these groups because they have some special names. The group 1 elements are called alkali metals because these form strong alkalis with water. The group 2 elements are called alkaline earth metals because they form weaker alkalis as compared to the previous group. Now moving on to group 13. This group is called the boron family because boron is the first member in the group. Similarly, group 14 is called carbon family, and then you have group 15 as nitrogen family, and group 16 is called the oxygen family, or also known as chalcogens, which means ore forming. Now group 17 is called the halogen family, and the last group, group 18, are known as noble gases or inert gases. Till now, our focus has been from element 1 to 20. So till calcium. Now let's go ahead and take a look at the full periodic table. In the complete periodic table, we have 7 periods or 7 rows and 18 groups or 18 columns. Now if you look at period 6 and 7, you'll notice something interesting, that elements with atomic number 57 to 71 and 89 to 103 are put separately below the periodic table. This is done to compact the periodic table. The elements 57 to 71 are called lanthanide series because they start with the element lanthanum. These elements are rare earth elements. And elements from 89 to 103 are called actinide series because they start with the element actinium. These are radioactive elements. Now let's discuss the merits of the modern periodic table. The merits are that it corrected the anomalies in Mendeleev's periodic table. Now how did it do that? Because Mendeleev's table was based on atomic mass, but the modern table is based on atomic number. It's based on the modern periodic law, which states that the properties of elements are a periodic function of their atomic number. So let's take a look how the anomalies of Mendeleev's table were corrected. First, let's talk about isotopes. Isotopes are atoms of an element having same atomic number but different mass number. They have identical chemical properties. Now, isotopes could not fit into Mendeleev's periodic table. But in the modern periodic table, they fit in nicely because they have the same atomic number. So, isotopes of an element belong in the same position as the element. And that makes sense because they have same chemical properties. The second point is Mendeleev had to make certain exceptions for some elements. But these are fixed in the modern periodic table. For example, the position of cobalt and nickel. Cobalt should come first because it has a lower atomic number as compared to nickel, even though it has a higher atomic mass, because the modern periodic table is based on atomic number. Even though hydrogen is placed in group 1, it's given special treatment. Many times it's shown broken off from group 1. Now why is that? Because hydrogen shows properties that are similar to group 1 elements, that is alkali metals, and also group 17 elements, that is halogens. So since it shows properties of both these groups, it's given special treatment. Friends, I hope you feel that you have mastered the modern periodic table now. Remember, practice makes you perfect. So I would recommend you to draw out our mini periodic table a couple of times and learn the first 20 elements. Now, trends in the periodic table will be covered in a separate video, where we look at how the properties change across the period and down the group. And do remember to subscribe to my YouTube channel and follow my Facebook page. And do check out my website, manochaacademy.com. Friends, be sure to try the quiz and the top 3 questions for this topic. Links are given below the video. Thanks for watching.